Hello guys, we are from Group 10 and welcome to our video presentation on the CFD and FEA study of a branch angle pipe junction. My name is Kwang Honjun and I will be opening today's presentation together with my teammates Nurul Muriza, Muhammad Juhimi and Lojime. We each took charge of simulating a specific pipe diameter ranging from 40 millimeters to 80 millimeters to conduct a comprehensive structural comparison. So here is the project background. The branch pipe junctions as shown on the screen are fundamental components in engineering piping systems. However, when highly velocity fluid merge at these anchor junctions, it creates drastic variation in pressure and velocity. This internal flow variation directly induces the mechanical stress and deformation on the pipe walls. To visualize and understand this heightened physical behavior, we derive advanced computational tools CFD for fluid flow analysis and FEA for structural. And this will lead to our purpose statement. The flow behavior at this Y junction is highly complex. If a piping network is not properly designed, the localized pressure concentrations can lead to structural failure over time. Furthermore, the exact effect of changing the pipe internal diameter on the stress and deformation isn't fully understood. Since we cannot easily measure these extreme internal forces in real life, numerical analysis is absolutely required to evaluate the structural integrity safety. To address this, we set four clear objectives for our project. First, to analyze the flow behavior using CFD. Second, to evaluate stress and deformation using FEA. Third, to explicitly identify the critical stress regions. And finally, to investigate the influence of varying pipe diameters. I will now pass the videos over to my teammate who will explain our methodology. Thank you.
My name is Nur Abza binti Ali. Now I will continue with the methodology. First, we started with geometry creation and also the mesh, which is for coarse, medium, and also the fine mesh. And then we continue with CFD analysis and also a grid independent test, which is the test is velocity, magnitude, and also the pressure. Then we continue with FEA analysis and also validation. And lastly, we compare the result with all the pipe diameters. Now, for the geometry and the boundary condition, the parameter we use is for type of fluid is water. The inlet velocity is 4 meter per second, and outlet pressure is 0 Pascal. For pipe thickness is 3 millimeters, and for the type of material solid is structural steel. Now for the grid independent test, we use the CFD verification. At my right is the value of the pressure and at my left is the graph of velocity magnitude. We ensure all case variation is less than 5%. And most of our pipe diameters in our project use the fine mesh as the mesh we use to do the next analysis. Now, this slide shows our CFD simulation result for the pipe junction. On the left, we have the pressure contour. The colors show how pressure changed through the pipe. The orange and the red areas indicate higher pressure, which we can see concentrated right near where the branch meet. On the right is the velocity distribution. Here, the green and yellow sections show where the fluid is moving fastest. As you can see, that's right at the junction point, where the two flow paths merge into one. This makes sense physically. When two streams combine at the junction, the flow gets squeezed and accelerates, which is why we see the highest velocity right there. At the same time, that merging creates turbulence and flow mixing. And the resistance from this mixing is what causes the pressure to build up at the same spot. Now, for the next slide, I will show you the example of the flow of pressure contour and also the velocity distribution.
On this slide, the FEA results are present through the stress contour and deformation contour. For the stress contour, the highest stress is concentrated at the pipe junction area where the fluid flow merge. This indicates that the junction is the most critical region and has the highest potential for the structure failure. For the deformation contour, the maximum deformation occurs near the unspotted shear region. Although the deformation is present, the value remains relatively small, indicating that the structure maintains good rigidity under the applied loading condition. Okay, for the FEA validation, we must compare our simulation stress against a manual hoop stress. First, we find the hoop stress using formula P d over 2T, which is P is average static pressure, D is diameter of the pipe, T is the thickness, and we get the hook stress is 0.414 megapascal. And then for the FEA simulation result, we get the 0.688 megapascal. And then we compare the simulation result and the hook stress result.
Next, I will discuss the comparison of maximum stress for different pipes diameters. Based on the graph, the maximum stress generally increased as the pipe diameter increased. For the 40 mm pipes, the maximum stress is 0.206 megapascal. The value increased to the 0.586 megapascal for the 50 mm pipe and 0.588 for the 65 mm pipe. The highest stress is recorded for the 80 mm pipe, which is 0.688 megapascal. These trends show that larger pipes diameter experience higher stress because a larger internal surface is exposed to the fluid pressure. As a result, the structural load on the pipe will become greater. Therefore, the 80 mm pipes produce the highest stress among all the pipes diameter investigated. Besides stress, we also compare the maximum deformation for each pipe diameter. The results show a similar trend where deformation increased as the pipe diameter increased. The 40 mm pipe recorded the lowest deformation of 0.0137 mm, while the 80 mm pipes record the highest deformation of 0.0548 mm. This happened because larger diameter pipes have lower structural stiffness and are not susceptible to displacement under the same pressure loading. Although the deformation increased with diameter, all deformation values remain very small and do not indicate any structural concern. Overall, the result clearly showed that pipe diameter has a significant influence on the structural response of branch pipe junction. All the cases, the 40 mm pipes produce the lowest stress and deformation, while the 80 mm pipes produce the highest value. In addition, the FEA analysis identified the junction region as the critical region for all pipe diameter. This is because the junction experiences a sudden change in geometry, which causes stress concentration and non-uniform load distribution. Therefore, special attention should always be given to the junction area during pipe design and structural assessment.
For the conclusion is CFD and FEA analysis were successfully performed. Flow mixing and pressure concentration occur at the junction. Stress and deformation increase with pipe diameter. Junction region is the most critical area. All stress value remain below the G strength of structure steel. The pipe design are structurally safe under the specific operating condition. That's conclude our presentation. Thank you for your attention. If you have any question, you can reach us by WhatsApp or email.